All right, now let's look at the Bronsted-Lowry acid-base definition. This is the one that we're going to use most extensively and the one that is more widely used than the other definitions of acids and bases. So in Bronsted-Lowry, we're looking at proton transfer. So remember, H plus is just a proton because a hydrogen ion, I'd have my proton and an electron. But H plus is missing that electron, so I'm just a proton. Okay, so we call that H plus ion a proton. So acid donates a proton, and the base accepts a proton. So acids still have to have H in their formula in order to donate that proton. But all a base has to have is a lone pair with which it can accept that proton. So under the classical definition, it's hard to classify ammonia as a base, but we know that ammonia is a base. If I look at the Lewis structure of ammonia, it looks like that. Oh, well, there's a lone pair that can accept that proton. So here's a couple examples. So here is hydrochloric acid. Okay, the lone pair on this water is going to yank that proton off of the hydrochloric acid, and we're going to end up with chloride ion and the hydronium ion. Here's ammonia. It's going to yank a proton off of the water. So the water is going to be the acid and the H plus donor. And I'm going to get the ammonium ion and the hydroxide ion. So what's interesting here is you can see that water can act as both an acid or a base. That's going to become really important later on. But again, what we have is a proton donor and a proton acceptor. Okay, a proton donor and a proton acceptor. And so when I look at the other side, my proton donor, that chloride ion now has one less H on it. Okay, my proton acceptor, my hydronium ion, now has one more H on it.